will be, there's a folder on Blackboard that has these blank sheets if you want to print them out and bring them, or you can just follow along and listen or write your own notes. Right now they're not there yet because they just changed these computers and I didn't have the right directory set up, but by tomorrow it should all be synchronized. So the first thing we're going to talk about is uncertainty and measurement. I mentioned this during the pre-test thing, that significant figures in science are not just about some weird rules so that we always get the same numbers. It's about uncertainty and measurement. It's about the proper amount of precision. And that comes from the tools that we use in the lab. Some tools are more precise than others based on how they're developed and how they're calibrated. And we need to take our measurements properly with the proper amount of precision. So whenever we take a measurement, we write down all the certain digits, the digits that we absolutely know are indisputably for sure correct. And then we write down one more digit that is an estimate. It's uncertain. It's our own estimate. And that digit is called the uncertain digit. So in a recorded number, an uncertain digit is going to be the rightmost, whoa. This has got like a smoothing thing that is kind of messing up here. Let's try that again. Okay, this is not great. Must be a memory thing. These computers are new, so I'm not sure what they're doing, but let's turn that smoothing off so that we don't have that issue anymore. Let's see if that's any better. Nope. Try one more thing. Fun of new equipment. All right, let's leave that like that, but then let's go with, where's the, there's a thing about smoothing that you can turn off.
Maybe you could go to the help.
I just changed it, because it was working. Let's try that and let's see. All right, I'll just write slowly for now. We'll figure it out later. Okay, so the rightmost digit when you write your thing out is going to be the uncertain digit. That means that that's the one that we are guessing at. And what that means, and how we do that in practice, we're going to look at a couple examples here. So the thing on the left, we'll say that's a graduated cylinder. You've got a liquid level that is right here, right? And we always measure, try a different color, to the very bottom of that shape, that curve. So the very bottom of that curve in the middle, we are going to look at the scale and we're going to determine what are the certain digits, which numbers are we sure of, and then what is the uncertain digit that we're guessing. So in this case, I'm going to say, well, I know that it's greater than 70, right? Everybody see that this measurement is greater than 70 but less than 80. So we can be pretty sure that that first digit, quite certain, is going to be a 7. Do you all agree with me there? Yeah. I would also say with pretty good certainty, even though I couldn't get the pen to really make it nice there, but I would also say with pretty good certainty that this, oh, you can't see my mouse here. There we go. I wonder if I can. No, we'll just use the mouse then. So you can also see that this is for sure above that third tick. Would everybody agree with me? That liquid level is above the 1, 2, 3, the third line above 70. So that means that our next digit is going to be a 3, and we're going to be pretty certain about that as well. So that would be another certain digit. But that's where our certainty ends, because there's no little lines in between. You see that? There's that line, and then there's nothing else until the fourth line. So we don't write 73 here. That's not the correct measurement, because we need to write one more uncertain digit where we essentially guess at where we think that is in between the two. So if you're looking at that line here, ignore what I drew, but you're just looking at those lines. In fact, just erase this. Just looking at that liquid level, what would you say? Would you say it's halfway between the two? Would you say it's a little bit closer to the top one, closer to the bottom one? What do you think? Where would you call it? Somebody shout out some numbers. 3/4 of the way, so like 7 maybe. Between 0 and 10, you'd say 7. Somebody say 6 maybe. 8, 5. Does those all seem like what you would, how you see that? And those would all be correct. So let's say somebody said about 3/4 of the way, so let's say 7. All right, so we're going to call that measurement 73.7. Those first two digits then are certain. We're sure of them. We know they're absolutely correct. And then that last one is uncertain. And we'd say like plus or minus 1, right? So it's probably between 6 and 8. That level, it seems to be halfway, at least halfway. So between 6 and 8, that seems like a good estimate. So that's the correct way to report that measurement. And that measurement is going to have 3 significant figures, the 7, the 3, and the 7. It would be incorrect to say 73.70 or 73.700 or 73.7000. Even though those seem like the same numbers, those are totally different levels of precision. Let me show you why with my poorly working pen. Really, I gotta, oh, there, that's the thing I was looking for. Okay, let's try that. It's a little button. So 73.7 really means that we're between 73.6 and 73.8. When we write a scientific measurement of 73.7, we are saying it's somewhere between 73.6 and 73.8, plus or minus 1 on the uncertain digit. So if we wrote 73.70, what does that mean? What? Well, it's another level of certainty. So what's the range? Yeah. Right, 73.69 to 73.71. So the difference up here, and difference is often shown by a triangle, a delta, a Greek letter delta. The difference is 0.2 in, let's say, milliliters. Let's say that's a graduated cylinder. The difference here is 0.02 milliliters. So a 10-fold difference in precision. So if you're rating that measurement as 73.70, you're telling whoever you're reporting the data to that you have a 10-fold more precise instrument than you actually have. That you used a 10-fold more precise thing to measure that than you actually did. And that's why that's an important distinction. Okay? Because it tells somebody who's looking at your measurement a totally different story about how you did that measurement. All right, so let's try these next two now on your own. Use that same rule. So you're going to look for the certain digits and then one uncertain digit. And you're going to come up with a measurement for this thermometer and then this other graduated cylinder here. Can you see those lines okay on there on the screen? You want me to zoom in?
Yeah, can you zoom in?
I think I can zoom in a little bit. Okay. So how would you write down those measurements? Write something down and then we'll talk about it. Everybody got some numbers written down? I want you to commit to it. Got to write something down. Don't be afraid to be wrong, but you got to write something down. Remember, tomorrow we're in lab, so you're going to be taking measurements tomorrow. So you got to know what we're doing. Everybody got something for each? Okay. So this temperature, how did you write this temperature? Anybody? Doesn't have to be right. I'm not going to put your name down. Just shout out a number. What'd you get? 88.4? Okay. We get something different? 88.2? Okay, 88.2. 88.3. Anybody get something different? What? 0.5. Anything else? Anybody get like something way off? Totally different? No? Okay. So let's go through it in the same way. We know for sure it's more than 80, so we write down that first 8. Then we count 1, 2, 3, 4, 5, 6, 7, 8. So it's for sure past that 8 one. And then it's a matter of where we're going to put this. This thing isn't exactly in the right calibrated thing here, but it's where we're going to say that that line ends. Now I'm closest to it, so I can probably see it the best. But when I look at that, I see not quite halfway. You can't see that. So I see that it's not quite halfway, right? So I'd see, yeah, any of these probably would be good. 88.5, when I'm looking this close to it, is maybe would be a little bit higher, but if I weren't looking that close to it, I could totally see that. So those would all be reasonable. And they are all within about 0.1, right? So each of those is a range, so they really overlap. When we say 88.3, we mean between 88.2 and 88.4. When we say 88.5, we mean between 88.4 and 88.6. So those are actually overlapping measurements. So great, good job. What about this next one? How would you call this one? 648. Anybody get something different? 649. What else? Anything way different? No? Good? Okay, so let's look at this again. This time we've got 600 here, and each of these lines is, we have to go back down here to figure that out. Each of those lines is 10. So we know it's above the 600. We know the 6 is correct. And we know it's above the 1, 2, 3, 4th tick. So those are our certain digits. That means our last uncertain one is wherever we guess this to be. And I would say, yeah, it's somewhere close to the edge there. So 648, 647, 649, something like that would be fine. So that's the correct measurement here. Okay. This is important because you're going to be doing this every single day in lab. Well, every other day in lab. Anytime we take a measurement with a graduated cylinder, with a thermometer, with a burette, all of the different types of apparatus that we're going to be using in the lab, we need to read them in this way and make sure that we're writing down the correct number of digits. And if you have a question about it, just ask. That's fine. But we need to make sure that we always take those correct measurements. It's not enough to just look at that and say, oh, it's about 650. We'll just say 650. That's not the appropriate way to take a measurement scientifically. What if it's a digital readout, like on a balance? What do you do about it on a digital readout? Any idea? Round? Well, you don't want to round because then you're limiting yourself on some precision. That's a good idea, though. But actually, on a digital readout, that uncertainty should be built in. So if a balance says 1.234, that last 4 is already uncertain. So if you're weighing something out and you see that last digit flickering, like between 3 and 4 and 5, 4, 3, 4, 3, 4, 5, 4, have you seen that sometimes? That's because that's an uncertain digit. So you don't really have to wait for that to settle. That's already uncertain. You just pick whichever digit you like and you write that down. But you're not going to guess an extra digit beyond what's digitally read. Okay, so feel like you can do that? Great. Some of the Mastering Chemistry stuff and the book problems have this kind of thing in there, so you'll get some practice as you work on the homework. Okay, so now this is often a little bit confusing, but all of those digits are considered significant. even the uncertain one. So the significant figures are all the certain digits plus the one uncertain one. They all count as significant. So when you're looking at how many significant figures your measurement has, you need to include all of those. And then as we just talked about, that uncertainty is going to be plus or minus 1 unless shown otherwise or noted otherwise. That last uncertain digit. You'll notice some types of glassware and things will say right on there what the measurement is, plus or minus 0.2 or plus or minus 0.5. So sometimes it's a little bit different. If it's not specified, we're going to assume it's plus or minus 1 on that final digit. Okay. So who's heard about this difference before? Precision versus accuracy. You heard this? All right, so where would you put those in these two definitions? One of them is the agreement of a given value to the true value, and the other is the degree of agreement among several measurements of the same quantity, or the reproducibility.
First precision, second accuracy.
What do you think? First precision, second accuracy? You gonna flip those? Yeah, it's confusing because these are words that we use interchangeably in real life. Like if you say that something is precise versus accurate, that basically means the same thing. But in science and in measurement, we have to make this distinction. So in this case, it's actually that accuracy is this first one, the agreement of a given value to the true value. And then precision is the degree of agreement. So let's look at what that looks like in practice. Here are 3 students' measurements in a class. Which of these, so they're measuring some mass, all right? And the true mass is 10.00, say, or 10.0. 10.00, yeah. Which student is accurate but not precise? Based on those definitions, which student is accurate but not precise? Good. A. Why is A accurate but not precise?
Because the average is closer to the real one, but his estimates are kind of.
Right. So this one is accurate, not precise. It's accurate because their average is pretty close to the accepted average. They got pretty close to 10. But it's not precise because the different trials are all over the place. This is what we call random error. Did I put that on here? This is what we call random error. Right? Stuff is randomly throwing this person off, but overall they're getting the right average. And that could be because of equipment, that could be because of technique, I don't know. So then which one is precise but not accurate? B, the next one. So this one is precise, not accurate. This person is getting really nice reproducible data over and over again. They're getting really, really close, but they're always off by about the same amount from the accepted value. And that's called systematic error. So maybe they're doing something a little bit wrong, but they're doing it the same way every single time. Like they're trying to dispense a certain amount of water, but they leave a drop in every time instead of getting that last little drop out or something like that. So they're doing it reproducibly, but there's something off, or maybe the glassware isn't calibrated properly and it's just not quite measuring the right amount. I guess it's a mass, so maybe the balance isn't calibrated properly or something like that. But they're doing the same thing, getting precise data. So then that means that the final one, student C, is going to be what? How would you describe that? Yeah, this one is going to be accurate and precise. Make a smiley face. Yay. That's what we all want to be. We want to be accurate and precise. We want to get the correct value, and we want to do it reproducibly every time. All right. So significant figures. let's do a little bit of review on that. I'm not going to go through every little rule all the time. I'm going to assume you sort of know that. If not, make sure you just go and review that a little bit. I'll write down some numbers. How many significant figures do we have in this first one? 4. Right? So every one of those digits is significant. How do you know?
Because they all like change value.
Right. So the general rules are all non-zero numbers are significant. Zeros in between numbers are significant, and zeros after a decimal place are significant. At the end after a decimal place are significant. So zeros before numbers or after whole numbers but before decimal places are not significant. And we'll talk about why that is. So let's look at this next one. How many significant figures in this next one? Just 1. Only that final 2 is significant. These other zeros are placeholders. They're telling you, like, what realm are we measuring in? We're measuring in that, let's say this is distance, and that's a measure of meters. So we're measuring in the millimeter realm, right? In the fractions of a millimeter, or the micrometer realm. But it doesn't tell us anything about the precision of the measurement. So 0.0002 is not more precise than 0.2. We're just measuring in a different range. We're measuring small things instead of big things. But it's the same amount of significant figures, same number of significant figures. Similarly, what about this next one, 10 million? How many significant figures there? Again, just 1. Right? Those zeros after that 1 are not significant because they're not a measure of precision. So that means if we write down a number as 10 million, we're saying this is somewhere between 9 million and 11 million. It's a big range, but if you're carbon dating something from 600 million years ago, it's not that big of a range. So maybe that is your precision. You're just measuring in a different realm, a different magnitude. Big things instead of small things. Okay, so this one got a little bit weird, but what if we measure 100.0? How many significant figures in 100.0? Not 1 this time, because that decimal point changes everything. So it's actually 4. All 4 of those digits are significant, because that 100.0 tells us that this number is between 99.9 and 100.1, right? Plus or minus 1 in that last digit. So that's a very different range. If we just say 100 point with no decimal places, or with no digits after the decimal point, it's kind of a weird way of writing it. I don't know if you've seen that before, but the reason we do that is we want to show that all those numbers are significant. So maybe you did a measurement and you got 100 exactly, but it's not 100.0. It's just 100 exactly. That's the most precise you can be, and you want to show that you're actually being that precise. You might put a little dot after that to show that all of those digits are actually precise. So that would come up in something like this. Let's say we had this device, right, which we know we can get 3 significant figures from this device, whatever this is. Let's say that line happened to settle right exactly on the 600. Well, if we just write 600, then we're not reporting the correct amount of precision, because we're only reporting 1 significant figure. So we might write 600 dot to show that all those digits should actually be significant. And then, as we just discussed, if we only write 100, we're only reporting 1 significant figure. So we don't generally want to do that, unless that is our precision of our measurement. Since this 100 dot is a little clunky, and what if it's like at the end of a sentence, and you don't know if that's a dot or a period? What's a better way to express that? Anybody know? What's a better way to express precision of a number like that than with a little dot at the end? Yeah, use exponential notation or scientific notation. So this 100 would be 1.00 times 10 to the 2 in scientific notation. And because it's 1.00, we can clearly see that there are 3 significant figures there. And then the scientific notation tells us about the range. So that would be true for all of these numbers. Instead of this one, we might report this as 1, just 1, times 10 to the, let's see, 1, 2, 3, 4, 5, 6, 7, 8. Is that right? 8. No, 7. 1 times 10 to the 7. To show that exact precision. So you may see that also. That's another thing to review if you haven't done a lot of that recently. We'll be using a lot of scientific notation, so make sure you're good with that. All right, so then let's look at what happens when we do arithmetic with significant figures. And this was on your test. We talked about this briefly. Multiplication is the easy one. Multiplication, division are the easy ones because you just use the significant figures of your least precise point, or the thing with the fewest significant figures. So if we are multiplying, for instance, 1.052 times 12.054 times 0.53, I calculated that out and I got 6.7208. So you never get rid of any significant figures until after the whole thing. So you're going to punch all that in. And then we look at that result and we say, does that have the appropriate amount of precision based on what we measured? So to do that, we're going to figure out the number of significant figures in each of the things in each of the numbers. And then we're going to round to that. So how many significant figures in this one? 4. And what about in this one? 5. And then what about in this one? Yep, just 2 in that one. That 0 doesn't count, remember, because it's before the decimal place. So then how many significant figures should we report our answer in? Just 2. So that means only 6.7 how we should report that answer. And that's important because if we report all those other numbers, we're telling people that we have a level of precision that we don't actually have. We're telling people that our measurement is more precise than it actually was. And that's not correct. With addition and subtraction, it's a little bit different. Because you don't make new decimal places through addition and subtraction, we actually line everything up and we figure out which place is the most precise. And we can actually use that because we're not kind of artificially creating decimal places. So let me show you what that looks like. We're going to add up a bunch of numbers. I'm going to stack them right on top of each other with the decimal place all in the same spot. So we've got 2.345, 0.07, 2.9975. We're going to add all these up. So you can add those up if you want. I'll just tell you that when you do that, it's 5.4125. And our smallest or our least significant measurement here has only one significant figure, the 0.07. That doesn't mean that we cut everything down to the 5 because this is addition. So we can actually use those places, which is why we lined them up so nicely with our decimal place. We're going to put a little line behind the lowest precision one, which is that 0.07, and that's where we cut off our precision. So that means that these numbers here don't make it into that final measurement. They are too precise. So our final measurement should be 5.41. There's some practice with those in chapter 1. We'll be practicing that all semester because we'll always have to do calculations and we'll always be dealing with this. So rules for rounding, as we said, make sure that you don't do any rounding until actually the final result. If you're doing a big set of something, right? Don't do any rounding till the end. And then our general rules, just so we're all doing the same thing. Less than 5, the preceding digit stays the same. If it's 5 or greater, then you round up. So 121.45 rounds to, yeah, 121.5. This can get a little confusing because some fields do this differently than others, but the general scientific consensus is to do it this way. If you're in another class sometime and they say to do it the other way, where 5 goes down, don't stand up and say, "You're wrong. What are you talking about?" Because that may be acceptable in that circumstance. As long as we're all doing it the same way, that's what's important. Okay, so before we get into that, I want to talk about one more thing that I didn't put on here. This is also on the homework, and this is, if you don't get anything else from this class, at least get this, because nobody gets this. Nobody gets this at all, and it's really important. There are 2 words that we are going to use in this class: law and theory. Have you heard these words before? They probably do not mean what you think they mean. Or I guess I should say, you probably think what they mean is different from what they actually mean in a scientific setting. The reason for that is that these are words that we use in non-scientific settings, right? Law means a whole bunch of stuff. There are laws, right, that you have to follow, or that you should follow, or that you want to follow unless you can not get caught. But that's like a different thing from chemistry. And then this word theory also means something. In normal everyday life, it means something about having some ideas about things, that kind of thing. But in science, these have very, very specific meanings. Anybody know what they are? The scientific meanings of these things? Go ahead, I saw yours first.
Law is a mathematical equation that describes a phenomenon, and theory is a proven or mostly proven something that describes.
Okay, so a law is a mathematical description of phenomena, right? It's a natural phenomena, and a theory is something that describes it, or that what did you say?
Like describes the law.
Describes how the law works, something like that. Okay, yeah. How would you word it?
I thought it was that the law was like it's always proven. And theory is like in most circumstances.
In most circumstances, but maybe
not
not.
exactly proven, but accepted.
Okay, so like accepted. Yeah, so those are great ideas about that, and that's actually closer to right than what we usually hear. Most people, and maybe you, most people think that a law is something that is proven, and a theory is something that is still up for debate. Like when a theory gets enough evidence, it becomes a law. Have you heard that kind of a definition? And that's not right. Not right in a scientific context. That's not true at all. It comes from the fact that law has another meaning, right? Law means like a law, like a government law. And so when we're first kind of debating what's going to become a law, we call that a bill, and it goes through Congress and whatever else, depending on what country you're in. And then when it's all done and finalized, it's law. And so people think that's how it works in science too, and it's not. So in science, it's these definitions, and I want you to know these. A law is simply a set of observations. Often that set of observations is described mathematically, something like gravity, for instance, that we know that 2 objects will attract each other with this particular type of a force. But it's just a set of observations. So we look at something, we see something, it happens over and over and over again, and we formulate this law that whenever this thing happens, this thing happens. So that's an example of a law. Anything that starts, whenever this happens, or these 2 things will always do this. Or, you know, the law of, I don't know, let's make up a law. Who wants to make up a law? Doesn't have to be real. What might a law sound like in that context? Everybody thinks it's a good one? We can have the law of lunch. Law of lunch might be every time we eat lunch, we're not hungry anymore. I don't know if that's a good example, but that's kind of dumb. But you see the idea. There's like an observation. Every time we observe, if we observe a group of people and you're all going to eat some lunch, and we measure your hunger before and after lunch. Before lunch you're hungry, then you eat the lunch, and then you're full. And so we say, okay, Anytime somebody eats lunch, they get full. That's a law. Doesn't mean it's true. Doesn't mean it's true at all. We have to have evidence for that. Maybe we start doing more and more experiments, and we realize that people are eating, I don't know, salads, and then they're not full after lunch. Or whatever. I don't know what makes you not full. But a law needs evidence, and it can be proven or disproven based on the weight of that evidence. So the evidence for, evidence against, and then we find something that works. So there are laws throughout history that have absolutely been disproven as evidence mounts on the other side, right? So then a theory, as you mentioned, is how we might define a theory as the reasons behind the law, the reasons behind the observations. Okay. So let's stick with our weird lunch example. If the law of lunch is that when people eat lunch, they're not hungry anymore, the theory of lunch might be the theory of calories, where we think that there are calories in this food that goes into our body and creates energy and makes us feel less full. Or the theory of stomach fullness, that as food goes into a stomach, it makes you feel less hungry. Right? Those are reasons behind the law. And those statements also need to be supported with evidence, and they can also be supported by good evidence or then defeated by evidence on the other side. So there's not a sense of like one of these is more true than the other. They describe totally different things. One of them is just a set of observations, what happens, and the other one is why is that thing happening? And that's a really important distinction, so that when somebody says, oh, that's not true, that's just a theory, you can say, well, actually that doesn't make sense in science. It's not how we talk about that. A good example of that is atomic theory. Anybody know what atomic theory is? It's a theory that everything is made up of atoms. Is that a controversial theory? Like, are there people saying, like, no, stuff isn't made of atoms. It's made of something else? Not really. We pretty much accept that stuff is made of atoms, right? And it explains all kinds of stuff. If we assume that stuff is made of atoms, we can explain all kinds of chemistry and everything else. So atomic theory is absolutely a theory because it's the reasons behind all these other things that we see, but that doesn't make it more or less true. It's true. I mean, it's widely accepted. But we don't call it a law now, right? A law is something different and applies to something different. So keep that straight. There's actually some homework problems about that. That will absolutely show up on the exams. And this is the weirdest thing that happens. It's not the weirdest thing. It's a weird thing that happens. We just spent, I don't know, 10 minutes talking about this, right? If I asked you all what's the difference between a theory and a law, you could probably just tell me what I just told you, right? And you probably have it straight. In 4 weeks or whatever, we have an exam, and a bunch of people are going to revert back to the old definition, to the old, a theory is just something that is not quite true until it becomes a law. It's because when we have these ideas that are so deeply ingrained in our head, it doesn't matter how many times they're challenged, we still keep going back to that old thing. So try to keep it straight, put a star, put it on your refrigerator or something so it keeps getting reinforced. Try not to be that one. Try not to be the few that go back to that old reason and back to the old way of thinking, because this is the correct definition. Your book also talks a little bit about this in chapter 1, if you want some better examples besides lunch. So questions about those? Okay. All right, the last bit of chapter 1, sorry, 2 more bits of chapter 1. We got dimensional analysis and, and then talking about matter. Let's look at dimensional analysis. Who's done this before? Convert units, that kind of stuff. Yeah? All right, we're going to look at this a little bit. This is another thing that comes up all semester long. Some people really don't like it. It's kind of the thing that once you get it, once you practice it, once you have a handle on it, it's pretty easy. You're just going to get it every time. So let's talk about it now. Let's talk about some ways to do it, and hopefully it'll stay with us for the whole semester. One thing that we often need to do is to convert one unit to a different kind of a unit. Converting ounces to pounds, for instance, converting inches to centimeters, centimeters to meters, millimeters to centimeters. As we work in different measurement systems in different realms, we're going to need to do this a bunch. And not just between the English and metric system, but often between inside the same system, just as our measurements change or as our scales change. So couple of things to remember when you've converted units. First, we need those unit factors, those things that tell us how many of this is in one of this. Google is great for that, by the way. Anybody ever tried that? Google will always tell you these things. You can type in how many ounces are in a pound, and it'll just come up and tell you 16, all that. So that's a good reference for that. You're going to figure out how to put the stuff together, do the math, and then check the significant figures. All right, so let's do some examples. How many miles would you walk if you had to walk 10.0 kilometers? Now, you may know how many kilometers are in a mile, but let's pretend that we don't know that right now. And we just have these factors to help us out. Because those are the only factors we can do. We can only take steps that we have in this particular list of factors. So that means we're going to go from kilometers to meters to centimeters to inches, then to feet, and then to miles. Everybody see how I came up with that plan? We have to step from one unit to the next. And if these are the only unit factors we have to step from each factor as we have it. So the only thing we know how to get to from kilometers is meters. That's where we got to get to. The only thing we know how to get to from meters is centimeters, so we go that way, and we keep going until we get to miles. Once we've got this plan, we're going to set up an equation to multiply and cancel the units to get there. So this is called the factor label method. Sounds like some people have done this sort of thing before. You're going to set everything up in a row so that the units cancel in the way that you want them to cancel. In this case, we're going to start with 10.0 kilometers. And we're going to multiply by a series of factors. Each factor, we're going to cancel the unit by putting it on the bottom of the unit factor and get the new unit by putting it on the top. So if we want to go from kilometers to meters, we put the meter on the top and the kilometer on the bottom. And our unit factor tells us that there are 1,000 meters in every kilometer. So that's what our first unit factor looks like. Now notice I put the units on there before I put the numbers on there. That's a good way to make sure you don't have these things backwards, because it's easier to get the units in the right spot and then just put the numbers in as they appear on the equation. So we're going to keep doing that. Our next step then is to go from meters to centimeters. And our unit factor tells us there's 100 centimeters in a meter. Then we're going to go from centimeters to inches. Then we're going to go from inches to feet, 12 inches in 1 foot. And then we're going to go from feet to miles. There are 5,280 feet in 1 mile. To get a final answer from all that then, we multiply by everything on the top and divide by everything on the bottom. So go ahead and try that, just to make sure you can do it, and then I'll write down the answer that I got. And I'm going to write it without doing the significant figures first, and then we'll go back and look at that. So I get 6.2137 miles, thereabouts. Is that what you got?
For the inches and centimeters,
Yeah.
Shouldn't be as an inflict. Yeah.
Oh, yes, you're right. You're right. Thank you. Yeah, centimeters smaller than an inch. So, absolutely. So now is that what you got? Okay. So is that the correct number of significant figures? How do we figure that out here? So we've got a bunch of different numbers. The what? Why is it the 10.0 kilometers? Yeah, right. Yeah. Well, so what we see here And this can be a source of confusion because, like, if I asked you how many significant figures are in this number 1,000, you would say just one. So we should just have one number. That's actually not true with these conversions because those are called exact quantities. Oops, I don't have that on here. Those are called exact quantities, meaning that there are exactly 1,000 meters in a kilometer by definition. So that's 1,000.0000000, however many zeros you need. It's exactly perfectly that quantity. Same thing with 12 inches in a foot. It's not a measurement of how many inches are in a foot. It's by definition exactly 12 inches are in a foot. So we can't use those numbers to determine significant figures because they're not measurements. They're exact quantities. So not measurements, exact quantities. The only measurement here is actually this one. Oops, you can't see that. Sorry, this 10.0 kilometers. So that's what we determine our significant figures from. And how many significant figures is that? 3. So that means that our answer should have 3 significant figures, or 6.21. So our answer here should be 6.21 miles. We should also note, usually when you go between systems, like metric to English, usually that conversion is also a measurement. So you could use that for significant figures. In this particular case, there are exactly 2.54 centimeters in an inch. So not that it would change our answer anyway, but you'll see that sometime. This also comes up with periodic table. You'll notice all those masses on the bottom. When we start doing mass calculations, you can pick however many significant figures you want. You can go look up those numbers to a whole bunch of significant figures usually. And so we will usually just use however many significant figures we need for the actual measurement. So if it says 5.0 grams of carbon dioxide, we would use 12 for carbon, and we would use 16 for oxygen because that would just be 2 significant figures. All right. So this conversion thing, hopefully it's something you've done before, something that you have some familiarity with. If not, please look through chapter 1 and work out some of those practice problems. There's a whole bunch of them. There's a lot of resources on the internet for that as well, factor label method or unit conversions, so you can get up to speed on that. Questions about that? Okay. So we're going to do one more style of conversion that's not exactly the same, and that is temperature. Let's see, should we do that now? Yeah, we'll do that now. Okay. We got 3 temperature scales that are important to us. Kelvin is an important scientific scale. What's important about Kelvin? Have you ever used Kelvin before? What's special about Kelvin? You can use it in a bunch of chemistry equations, yeah. That's true. What else about it?
Starting point is like freezing the boiling point of water or something?
Not quite. You're thinking of I think you're thinking of Celsius. Kelvin, the starting point is absolute 0, which means there are no negative numbers in Kelvin. So it goes 0 is absolute 0 means that there is no molecular motion whatsoever. Doesn't really exist. We get really, really close to it, but you can't quite get there. But that scale starts at 0, which makes it really useful in a lot of calculations. And so we'll be using Kelvin for that. It's also nice when you're measuring really cold things. In our normal life, we mostly use Celsius and Fahrenheit. Fahrenheit, of course, is what temperatures are reported in the news and what we use kind of popularly. When we say it's 80 degrees outside, we're talking about Fahrenheit. And then Celsius is what we use more in the lab, and other countries around the world tend to use. Because it is that 0 to 100 scale, fits pretty nicely. So what's the boiling point of water in Celsius? You know, boiling point of water in Celsius is 100. What's the boiling point of water in Fahrenheit? You know that one? 212. What about the freezing point of water in Celsius? 0. Right, so that's why Celsius is so useful. Water, it's based on water. If water freezes at 0, water boils at 100. Where does water freeze in Fahrenheit? 32. So you got a little bit weirder scale of 32 to 212. for water. And then Kelvin is Celsius plus 273.15. So about 273. Remember that number, 273. So that means that the freezing point of water in Kelvin is what? Yeah, so the freezing point would be 273 and the boiling point would be 373. Right? And that number comes from the difference between the freezing point of water and absolute zero. That one's easy. That conversion's easy. You just add that number or you subtract that number, depending on which way you're going. The trickier one is Fahrenheit to Celsius, because you have a couple different conversions to do. You have to convert the size of the unit. So what's a bigger unit, a Fahrenheit degree or a Celsius degree? What's a bigger piece? I heard Celsius. Let me see Celsius. That's correct. Why? How do you know?
There's a bigger distance between 0 and 1. Sorry, it's bigger distance between 32 and 212 and 0.
Right. There's a bigger distance between 32 and 212 than 0 and 100. So the difference between 32 and 212 is what, 180 degrees, right? The difference between 0 and 100 is 100. So that means that a Fahrenheit degree is a little bit smaller. So we have to convert the size of the degree, and then we also have to convert the 0 point, because the 0 points don't line up, right? 0 Celsius isn't the same as 0 Fahrenheit. And that's one of the only times we have to do that. If we're talking about mass, 0 grams is the same as 0 pounds, right? The 0 points are in the same place. That's true for pretty much anything else that we measure, but in temperature they're not. 0 Celsius lines up with 32 Fahrenheit. So we need these equations that allow us to account for that difference in size of degree and also that offset point. All right, so I'm going to give you a couple equations for that. We're not going to go through the whole derivation. You can look at it in the book if you want. That's what the equations look like. So if you want to get a Celsius temperature from a Fahrenheit temperature, you take the Fahrenheit temperature and you subtract 32 to get to 0. And I'm going to rewrite this in a second because I don't think this is super clear. But you subtract 32 to get to 0, and then you multiply it by this 5/9 factor to make a Celsius degree out of a Fahrenheit degree. And then you're going to do the opposite for Fahrenheit. You're going to do the conversion first, this degree size conversion first, and then you're going to add the offset. This is a little bit of a confusing way to write it. Luckily, the book has changed a little bit. So I'm going to rewrite it for you up here in a way that I think is a little bit easier to see. So we're going to say that the degrees Celsius, this is the same thing, by the way. I just think it's an easier equation to use. The degrees Celsius is the degrees Fahrenheit minus 32 divided by 1.8. So 1.8 is that 9 over 5. So if we divide by 1.8, it's like multiplying by 5 over 9, for those of you who think about it that way. But I just think this is an easier equation to look at. If you don't, if you like these better, that's fine. Go with those. And then the counterpart to that is that the Fahrenheit degree equals 1.8 times the Celsius degree, and then plus 32. So that's how it's written in the book. I think that then you just need to remember that number 1.8, get it in the right spot, and you'll have those conversions. So let's try it. Normal body temperature is 98.6 degrees Fahrenheit. What is this temperature expressed in Kelvin? So how would we get from Fahrenheit to Kelvin? Is there an easy just Fahrenheit to Kelvin conversion? Not really. So what should we do first? Yeah, let's convert to Celsius. Which equation are we going to use of these two? The left or the right? Yeah, the left. Because we're starting with a Fahrenheit temperature, and we want to end up with a Celsius temperature. So let's plug that in. That means our Celsius temperature is going to be 98.6 minus 32, and then that number divided by 1.8. And that comes out to 37.0 degrees C. normal body temperature is 37.0 degrees C. If you do that out, keep in mind the order of operations. This is a common mistake. You can't just type in your calculator 98.6 minus 32 divided by 1.8. Because order of operations tells you we have to do division first. So that means that it'll divide 32 by 1.8 and then subtract that whole number by 98.6, and you'll get the wrong thing. You gotta do the subtraction first and then divide. Okay. So now we have our Celsius degree. How do we get to kelvins? Right, so we're gonna go 37.0 degrees C plus 273.15 K. By the way, kelvins don't have a degree. It's not degree Kelvin, it's just kelvins. It's like a unit, like grams. And that's going to come out to 310.2 kelvins. Because remember, for addition, we line them up and we use the smallest decimal place, and that 0.0 means we're going to keep the tenths place in our final answer. So it's going to be we're going to end up with 310.15, and then since we cut off at the tenths place right here, we're going to cut that 5 off and say, and round to 310.2. See that? All right, try this one on your own. And that'll be the last thing we do today. Outer space is about 4K. What is this temperature expressed in degrees Fahrenheit? Keep working. I'm going to write it down up here. If you're done, you can follow along. If not, just keep going. All right, do something like that. So look what I did here. I took the 4K and I subtracted 273.15. Significant figure rules tell us to cut off after the ones place here. So that gives us minus 269 degrees C. Then we're going to multiply that by 1.8 and add 32. Those are exact factors, so we don't need to consider them in significant figures. That gives us minus 452.47, which we then round to minus 452 based on the minus 269, 3 significant figures. So minus 452 degrees F. Look good? All right. So for tomorrow, we'll have lab. We'll do that pure volumes of pure substances additive. So make sure you have that printed out with the data tables, or at least print out the data tables, or put them in your notebook, and have the instructions digitally. I recommend printing it all out just because then you don't worry about spilling stuff on your devices, but that's up to you. We will start off right at 11 tomorrow and pretty much go into the lab. I'll tell you a little bit about pipetting, and then we'll do it. So yeah, oh, please turn, sorry, can you hold that up? So please turn those back in because we're going to reuse them. Just make a pile up here on your way out. If your safety quiz and form are done, you can turn those in too. If the quiz is not done yet because we didn't get a chance to go through some of those questions, that's fine. Just hang on to it. We'll do it tomorrow.